Sorry? Yeah.
Welcome everyone to Theory Lunch. Today we have Swaprava Nath giving a talk on efficiency and budget balance. Swaprava is a postdoc here with Ario, and his interests and works are on classical and computational social choice.
Thanks, Nika, and hi everyone. I'm going to talk about two very important properties of social choice theory, namely efficiency and budget balance. And we'll show how computational approaches can help understand the interplay between these two properties in a very precise manner. So this is a joint work with Thomas. And so I have kept the talk at a very basic level. So we'll start from scratch. But still, if something is unclear, feel free to stop me. So the plan is the following. We'll start with an example to motivate the problem. Then we'll formally present the model and talk about some well-known results in this space. Then we'll talk about deterministic and randomized mechanisms. This will make sense as we go along. So let's consider the following example. Suppose the city of Pittsburgh is trying to decide on whether to build a soccer ground or to build a library, and even restricted assumption that suppose there are only 3 individuals in the city, Alice, Bob, and Carol, and these numbers reflect what is the amount of satisfaction or happiness that they get when each of these alternatives are chosen. So we'll usually call them as the valuations of the agents. So in this case, if the soccer ground is built, Alice does not become much happy, so her valuation for the soccer ground is 10, while she is much more happier if the library is built. The assumption is that these numbers are known accurately to the agents. So these are private information of the agents. The planner who is trying to take the decision on whether to build the soccer ground or the library does not know this information, this valuation information. Now, even though the planner does not know, we'll use the term planner and mechanism designer, decision maker interchangeably. He wants to take a decision that is efficient in the sense that maximizes the social welfare, that is the sum of the valuation of all these agents. So in this context, if you take the sum of these numbers and these numbers, you can see that the efficient decision is to build the library. That's one of the classical properties of economic efficiency. But the problem here is the social planner wants to take a decision about which he does not know anything about. For example, these numbers are private to the agents, but the designer does not know anything about that. So the goal here is to solve a imprecisely defined optimization problem where the planner's goal is to take a decision that is efficient, but the information to take that efficient decision is private to the agents. So you can imagine a very naive approach of asking each of these agents. The planner asks each of these agents to report their valuations of all these alternatives, and then he can say, well, I'm going to take the decision that maximizes the social welfare. You can very easily imagine that is going to fail for sure, because now if Bob reports his valuations truthfully, then he knows that the decision is going to be the library, which he does not like at all. So what he will do is he will reduce the valuation for the library and increase the valuation for the soccer ground, and that will possibly give an inefficient solution, inefficient in the way that we defined before. So a large body of literature in the social choice theory essentially tries to see how you can capture the truthful information, how you can elicit the truthful information from these agents and also take an efficient decision. So you can think of a little more a sophisticated mechanism where I can take a decision irrespective of irrespective of the reports of the agent. So I can, the city planner can take a decision of building the soccer ground irrespective of anybody else's report. So that's a constant mechanism, but that is strategy proof because nobody has any, nobody has any power to change the outcome. On the other hand, if the planner says, well, I'm going to pick Bob or Alice or whoever, with a certain probability, he can pick one of these agents and pick his and decide in favor of his favorite alternative. So that is a kind of a mechanism which we'll call the dictatorial mechanism, and that is also very obviously truthful because the person who is the dictator has no reason to lie because his favorite outcome is chosen, and the others cannot change the outcome anyway. So, but these are the mechanisms which are not very interesting in the sense that they are not going to give an efficient outcome. So you can always create an example where the efficiency is arbitrarily bad for this kind of mechanisms. But now, and a bunch of literature essentially shows that if you don't have any other information available from them and you don't have, the mechanism is,
yeah. Yeah, I have a question about value functions. Are they bounded?
No. So in this case, the thing that we are going to discuss is, in this particular example, you can assume, well, what do you mean by bounded?
I think there's a cap on how much you can value one.
It doesn't matter. Yeah. So then, still, it will be. It will not be. So it will be truthful for the two mechanisms that I talked about. Yeah. So what I am going to say now holds even if it is bounded. Here I am not making any assumptions. So anyway, so if you don't have any other way. Yeah.
So this you're discussing in kind of a slightly more general setting than the people submitting preferences, right? So it's kind of like not just so they could submit either preferences or just not utilities for them or unbounded.
Yeah.
So it's a slightly more general setting than the standard kind of computational social choice.
Yes. So essentially, yeah. So in this context, I am not only assuming just the ordinal orders. I'm also giving some kind of numbers, which automatically will induce an ordinal order. But yes, so this setting is much more general. The preferences are more rich than just the ordinal orders.
But it will be the standard posilinear setting. It will be the total standard setting.
Yeah, so I'm just coming to that.
Yeah.
The literature in this space says that if you are not allowed to make any other kind of, if your mechanism is very naive and you cannot allow some kind of a transfer of utility, more or less this kind of determinist, the dictatorial ones or constant mechanisms are very much the mechanisms that you have. But suppose we could actually tax people. So now what we can do is we can take a decision, possibly the efficient decision, and also ask people to pay a certain amount of money. So then it turns out that a lot of things will start happening. In particular, I can take the efficient decision. And how the payoffs are going to change because of this introduction of money is in a quasi-linear way. So suppose the agent Alice, he has a valuation for this alternative A. The payment that he is going to make is PA, and the net utility or the payoff of agent Alice is just the difference between these two terms. And this is known as the standard quasi-linear preferences. particularly this is important because of two reasons. One is its simplicity, and the second thing is you can now take the efficient decision with the introduction of this thing called money. So I just told you how, I can take an efficient decision. How do I do that? So let's take the same example and now compute the outcome. So I'm going to ask each of these agents to report their valuations, and suppose these are the reported valuations. Then I take the outcome which is efficient, that is maximizes the sum of the valuations. Now I'll charge a certain amount of money to each of these agents. To compute the payment that Alice needs to make, I am going to assume that she is not in the system. Then what outcome would have been chosen? The outcome would have been the soccer ground. Because of her presence, the outcome changes to the library. Now, what is the net amount of the valuation, the sum of the valuation of the other agent is when she is not present, that's 100 plus 10, 110. And because of her presence, the sum of the valuation of the other agent changes to 60. So Alice is asked to pay just this difference. The net, the change in valuation that she is imposing on the other agents is what she is supposed to compensate with. And this is what is known as the pivotal mechanism. So why pivotal? I'm coming to that. So similarly, you can think of Carol, just exclude her from the system and compute the valuations that the other agents are going to get when she's not present versus when she's present, and that is the amount that she pays. Notice Bob, if he is not in the system, the outcome does not change. It was earlier library, it's still going to be library. So he is not pivotal in the sense that his presence is not changing the outcome from something else to something other. So because Bob is not a pivotal agent, he is not going to pay anything in this mechanism. So let me just tell you that this mechanism is going to be strategy proof, even though I'm not going to prove it. So this is a classical result from the social choice theory proved years back. This mechanism is known as the Vcg mechanism, and sometimes also this payment is called the Clark's payment, pivotal payment. So now what happened is I have taken the decision which was efficient, and also I have implemented this payment which makes sure that the agents are going to report the valuation truthfully. Yes?
You're taking the efficient decision now, but you use this information that you didn't have before about the preferences to figure out how much they pay. So isn't it?
I'm sorry. Yeah. So essentially, that's what I'm going to. So your point is essentially you are not looking at the total utility. So, you are not actually caring about the payment. Is that what your question is?
No, it just seems that you use these preferences to figure out what the payment is, and then you can do an efficient decision. But before you're not allowed to look at the preferences. Oh,
so that's what I have skipped. So you can actually even if you had something else, some other VI prime, you can always show that the valuation, the net utility is not going to be more than what you get if you report it truthfully. So this is something that I have not proved, but that's a standard result. I think a more interesting question is, I am calling this as efficient, but just looking at the valuations. But I just said that the utility of this agents is this valuation minus the payment. I'm still considering the efficient outcome to be the outcome that maximizes the valuation, and I'm not considering what payment these guys are making. So ideally, I would like to have a mechanism where this net transfer, where here the net transfer is 50 plus 30, 80. I'd like this net transfer to have 0, because I can expect someone to pay and someone to consume, but there should not be any net transfer, because that is going to change the sum of the utilities if you like. So and that is what is a necessary thing for this Vcg mechanism. You cannot actually have a case where for all valuations the net transfer is going to be 0. In other words, in order to satisfy the truthfulness of all these agents, you'll have to burn this amount of money. You'll have to destroy it. You cannot give it back to the agents because that is going to change their preferences again. So a very important question and a very important criticism about this VCG mechanism is, can we have a mechanism where you take the efficient decision, at the same time you don't have any money burning? And that is what we are going to talk about in this presentation. So is the mechanism clear? Because we'll be using this over and over again.
So you're assuming the government's not an agent, right? So you're not allowing the government to take the money or something like this?
No. So the decision maker has no stake in this, yes. Okay, so let's make the model a little formal. So we'll be assuming n agents and m alternatives. Each of these agents have a valuation function, which is a mapping from the set of alternatives to the open interval minus m by 2 to plus m by 2. So this is in this case it's bounded. Then the set of valuations of each agent, agent I is denoted by Vi, and by capital V will be denoting the set of all valuation profiles. The goal of the social designer or the mechanism designer is captured by this function called the social choice function, which is a mapping from the valuation profiles to the set of alternatives. And when we will be discussing about the randomized mechanisms, then it will be a mapping on the outcome would be a lottery over the alternatives. So pictorially, what it means is each valuation profile is a matrix that looks like this, where on the rows I write down the agents, and on the columns I write down the alternatives, and each of these numbers here is the valuation of that particular agent for that alternative. This social choice function essentially takes this matrix as an input and outputs one alternative or a lottery over the alternatives. So that's what the social choice function is. Now the payment function is a mapping from the valuation to the set of real numbers. Notice that the numbers can be positive or negative, which means the positive payment means that I am asking the agent to make a payment. Negative means the mechanism designer is paying the agent. And each agent's payoff is just the valuation minus the payment. That's a quasi-linear setting. And by mechanism, we'll refer to the tuple of these two functions f and p. So, now the formal definition of strategy proofness or the truthfulness in our setting is a mechanism f comma p is strategy proof if for every v minus I, the valuation of the other agents, agent I is always going to be better off by reporting his valuation truthfully. And the VCG mechanism that we talked about essentially is a strategy proof according to this definition. The valuations and the payments are such that even if you report some other VI prime, this is always going to be larger when you are reporting your valuations truthfully. The other property that we want is that of efficiency. The social choice function picks the alternative that maximizes the sum of the valuations of all the agents. The third property is that of budget balance. There's the sum of the payments is 0 for every valuation profile, for every V. And we'll be assuming one technical property, which is that of neutrality, which essentially means that if for a particular valuation profile, if the outcome was A, and now if you are just swapping the valuations of all the agents between A and B, now the mechanism will now start outputting B as an output. So essentially it means that the mechanism is neutral to the identities of these alternatives. All that matters is what is the numbers associated with these alternatives. And of course, the payments will not change in this context. So we'll be assuming the mechanisms that has these nice properties. So now, a classical result that has been proved way back in 70s is that all these nice properties cannot be satisfied together. So in the quasi-linear domain, if you are considering strategy proof mechanisms, then they cannot be both efficient and budget balanced. And the way that they prove is, first they consider the first two properties, the strategy proofness and efficiency, and show that this two together implies a particular class of mechanisms known as the Groves class of mechanisms. And in the second part, they show that this Groves class of mechanisms cannot be budget balanced in general. So this is a negative result for sure, but this does not tell you how far away are we from the efficiency. So even if I'm going to ask the question that look at all the budget balanced mechanisms, what is the best inefficiency? I know that it cannot be efficient. What is the minimum inefficiency that I can hope for? So this mechanism, this result by Green and Lafont does not talk about that, and that is something has been looked at in different contexts of mechanism design. So a little bit, we'll go back to the prior work in this setting. The strategy proofness constraint that we had is true for every valuation profile of the other agents. Note that this is a very strict requirement that no matter whatever the other people are reporting, it's beneficial for you to report your valuations truthfully. A weaker notion of that is when you have a prior. So suppose I knew that the valuation of all the people in this room is known a priori and we agree on that, distribution, then I can take the expectation of the V minus i's given my own observed VI. And if I look at that expected utility of mine, is it beneficial for me to report my valuation truthfully or not? So that, if it is true, then the type of mechanism that satisfies that property, we call that Bayesian incentive compatible. So in an expected sense, it's truthful, not truthful for every valuation of all the agents, all the other agents. And if you allow that weakness in the definition of the truthfulness, then there is a mechanism named after this people, DAGVA, which achieves the full expected efficiency and is also budget balanced, but it requires the knowledge of the prior, which is a consistent prior. Everybody agrees on that prior beforehand. So this is one way of getting around the impossibility result of Green and Lafont. Later, I mean, in the beginning of 2000, there had been a bunch of work by Konitze and Sandholm which shows that if you look at the optimization-based approach, so our goal is to minimize the inefficiencies subject to a bunch of constraints, budget balance, strategy proofness. You can actually pose this problem in that form, and for a particular problem setting, you can actually solve for the mechanism that is optimal in that setting. So that approach is known as the automated mechanism design approach, and I'll come back to that because I'll be using that in my later part of my work. So another way of getting around the impossibility result is to consider the Vcg mechanism and the surplus that is generated by the Vcg payments to efficiently redistribute it in a way such that it does not harm the strategy proofness constraint. It is not always possible, but in certain contexts, in particular for the multi-unit auctions or heterogeneous object allocation, it is possible to redistribute the payment given by the Vcg scheme back to the agents in a way such that it does not violate the strategy proofness constraint. And this bunch of paper essentially shows the case where you are fixing the efficiency as a requirement and trying to minimize the budget imbalance as much as possible. And later in 2014, Guo and Konitze has looked at the joint problem of inefficient allocation as well as budget imbalance together for a special class of problem settings known as the multi-unit auctions and for a very special class of allocation schemes. So what we are going to do in this talk is we are going to ensure incentive compatibility or the truthfulness guarantee in dominant strategies, which is prior free. So we are not going to assume any kind of prior on the valuations. We show a very tight lower bound on the inefficiency. In the first part, we just consider the deterministic mechanisms and look at the budget balanced strategy proof deterministic mechanism and give a lower bound on the inefficiency. And in the second part of the deterministic analysis, we look at the joint problem of inefficiency and budget balance together and see whether we can improve our inefficiency bound in any way. We finally show that in the context of randomized mechanisms, these bounds can be improved, and we'll talk about that near the end. So deterministic mechanism, remember it's a mapping from the valuation profiles to a particular alternative deterministically, and in the first part we'll be discussing about budget balanced and strategy proof mechanisms, but they are minimally inefficient. And the metric that we'll be using for measuring this inefficiency is that of a sample inefficiency. Note that the first number here is the maximum social welfare that you can achieve, the optimal thing that we want to achieve. But because we cannot have a mechanism which is both budget balanced and strategy proof and can achieve this one, possibly I have a mechanism which is budget balanced but does not achieve the optimal social welfare. So there is a difference. We look at the maximum difference in this social welfare and then normalize that appropriately. And this gives us a metric how good our mechanism is performing in terms of inefficiency. And when we go to the randomized mechanisms, we just take the expectation with respect to the lottery that is returned by the mechanism. And now the question that we are going to ask is find a budget balanced mechanism that minimizes this metric. So before I give the final result on the lower bound of this inefficiency metric, let's discuss one specific mechanism. And this is pretty intuitive mechanism. We call that a sink mechanism. So we have one or more sink agents. I'll come to that. So a bunch of nodes, a bunch of agents denoted by this S, which is a subset of the set of all agents, is called the sink agents. When I'm not using, the social planner is not using their valuation while taking the social decision. So in other words, I'm just ignoring their valuations altogether and taking a decision without looking at their valuations. But I'm also going to compensate them with the payment that the other agents are going to make. So I'm running the mechanism on the valuations except this set of sink agents, and then whatever surplus I'm going to generate, I'm distributing back to these agents who are sinks. So let's take one specific example. Suppose the set S is a singleton. I have only one sink agent. And I'm going to take the decision of picking the efficient allocation without this agent. So here I'm just summing over all the valuations of the agents except agent IS and taking the socially optimal for them, the decision that is socially optimal for them, and then charging them the Clark's payment rule, the VCG payment that we discussed in the beginning. I know that is going to be strategy proof because of the properties of the VCG scheme. And now I also know that is going to generate a certain amount of surplus, the money that I earlier used to burn, but now I can give this leftover money to the agent IS. Note that because I am using the VCG scheme in a world without IS, it's always going to be strategy proof for those agents. And for agent IS, it's also strategy proof because by misreporting his valuation, he cannot change anything. He cannot change the decision. He cannot change the payments. And so therefore, this particular sink mechanism is strategy proof and budget balanced by design. And you can compute that it has a sample inefficiency, which is 1 by n. So the good news is the inefficiency goes down. So the original result by Green and Lafont says that you cannot satisfy them together. Well, you cannot do it exactly, but as you have large number of agents, the inefficiency essentially vanishes. But one can ask, is this the best mechanism that you can have? So that's the question that we are going to do in the next slide. Can we do better? And the answer is surprisingly no. And this is a very non-trivial result that takes care of every deterministic strategy-proof budget balance and neutral mechanism. And we show that the sample inefficiency would be lower bounded by 1 by n. So you cannot really do anything better than that sink mechanism that I talked about. And how do I prove it? It's in 2 steps. In the first stage, if you assume this properties deterministic strategy-proof budget balance neutral, we show that there exists at least one sink agent. And the proof of this theorem uses a known result in the context of social choice theory, which says that if you are just considering deterministic strategy-proof and neutral mechanism, then the mechanism must look like something like this, which is known as the neutral affine maximizer. Just to read out how this is computed, you have a non-negative weight on all these agents. For all the people in this room, I have a non-negative weight, not all 0. And then we consolidate the weighted sum of these valuations and pick the alternative that maximizes this weighted sum. That is what this neutral affine maximizer is. But the result says something much stronger. It says that if you are going to design a deterministic strategy-proof neutral mechanism, that must be in this class of mechanisms. So what is an interpretation of a sink agent in this context? It is essentially an agent whose weight is 0. So just note that. Okay, so just to give a feeling of how these affine maximizers look like, if all the weights are equal, maybe without loss of generality 1, then I am taking the efficient decision, right? So efficiency, the efficient social choice function is a special case of neutral affine maximizer. On the other hand, if you had only one weight to be positive and everything else 0, then that agent whose weight is positive, he is essentially the dictator. I am just taking the decision which maximizes his valuation. So all these dictatorial and the efficient outcomes fall in this huge class of affine maximizers. And in this class, the interpretation of a sink node is the node who has weight 0, because if you have an agent whose weight is 0, his valuation is never going to be used in the social choice outcome, and you can show that the payment that he gets is essentially the function of other agents' valuations. So all that we need to show in order to prove that there exists at least one sink agent, we'll have to show that not all the weights can be positive. So having all weights positive is a contradiction to budget balance. That's how we prove this result. I'm just skipping the detailed proof for the interest of time. And now what we know is we have an agent who is a sink agent whose weight is 0. It's very intuitive, though we have shown it formally that if you have more sink nodes, it's only going to do worse in terms of inefficiency. More agents whose valuation you are not looking at, you are not going to take an efficient decision. So now to complete the proof, we'll have to say something about what happens to the weights of the other agents. And this lemma says that the lowest sample inefficiency will be found when there is exactly one sink node and the weights of all the other agents is equal. So in other words, it's actually pointing towards the mechanism that we discussed in the beginning. I'm going to have only one agent who is sink. I'll isolate him. I'll take the efficient decision without that agent and then transfer all the amount of money that is generated to this agent. And that mechanism is the optimal mechanism which minimizes the sample inefficiency. So that's the result in the context of deterministic mechanisms. So
So you mean by creating a profile that is unbalanced, basically taking the person with the highest weight, like assuming it's slightly higher, and then make him kind of like a little less, like give him like a valuation that's relatively low to kind of like to make it unbalanced in that sense.
Okay, so you are talking about this, the proof of the lemma. Yes, yes. So essentially, if there is a difference in the weights, you can always create a valuation profile where the inefficiency would be worse. Yeah. So in the second part of this deterministic mechanisms, look at the the joint problem of inefficiency and budget imbalance together. So let me just get into the to the expression which explains it itself. So earlier I was just looking at the inefficiency term. So imagine when lambda is equal to 1, then this term is the same as the difference in the loss in the social welfare and then appropriately normalized. Now I am also taking care of the budget imbalance. So the sum of the payments, the absolute value of it, is what I am trying to minimize. Ideally, I would like to have a mechanism which does not have any budget imbalance, at the same time as low inefficiency as possible. Now I am posing the question jointly, and what we could prove is that that asymptotically this addressing this joint problem does not give you any advantage over what we did in the previous setting. So here also the rate of decay is lower bounded by 1 by n. Of course, this is omega because it depends on how you choose those lambdas. And the two extreme cases where lambda is 1 or 0, you have mechanisms which can drive this inefficiency down to 0. So this result does not say that for a particular n, you cannot have a better joint mechanism. It's just saying that if you look at the asymptotic case, this considering this joint problem is not any better than considering the case where the mechanism is budget balanced and we are trying to minimize the inefficiency. Okay, so that takes care of the deterministic mechanisms and kind of gives a very tight bound on what is the limit of inefficiency. Now, for the context of a randomized mechanism, it's a little trickier. So in this context, we are just looking at the first problem that we discussed in the deterministic case. We are talking about budget balance mechanisms and trying to minimize inefficiency. And a naive approach would be to pick every agent. There is a typo. So pick every agent as a sink with probability 1 by n. Pick every agent uniformly at random and treat him as a sink. That is going to be strategy proof, budget balance, and neutral by design. But maybe you can speculate that this is not going to give the minimum achievable inefficiency bound. The trouble in the context of randomized mechanism is that we do not really know the structure of the strategy proof and budget balance, even the strategy proof mechanisms in the context of randomized schemes. In the deterministic case, we had a structure which looks like an affine maximizer, but in the context of randomized mechanisms, nothing is known till date. So what we do is we take two different approaches. The first approach is we show lower bounds for a specific class of strategy proof, budget balance, randomized mechanism. And then in the second part, we look at finding the analytical lower bound of an optimal strategy proof. So now we are looking at the optimal mechanism. So it's not coming from a specific class. And to solve this problem, we use the techniques of automated mechanism design so that the problem can be posed as an optimization problem. And we'll see how these results perform. In general, we get in this class of special class of randomized mechanisms, we do have a better inefficiency, that is lower inefficiency than the deterministic case, but the optimal thing is even better. So and we are still working on that problem. Yes.
So I'm trying to understand why the inefficiency actually gets better in the worst case. The kind of example I have in mind is maybe one alternative has utility 1 minus epsilon for every agent, and then for every n minus 1 agents, there's an alternative that has utility 1 for these agents and 0 for the last one.
Okay.
So it seems like in the worst case, I wouldn't. So whatever agent I choose, the sink agent, I would choose one of the suboptimal alternatives.
So how many alternatives are
So
you
there
picking?
so I have for every, so I have n plus 1 alternatives.
So that's bang on. So this mechanism, this special class of the sync mechanism won't do well when you have more alternatives than agents. It's only useful when you have smaller number of alternatives. Yes, so yeah. Okay, so this class of mechanisms that we'll be calling the generalized sync mechanism. So it's a little general than what we discussed before. Instead of picking with a constant probability each of these agents as sync, I can now do it in a general way where I look at the valuation profile, whatever valuation profile has been reported. Depending on that, I choose a probability distribution over these agents, and agent I is treated as sync with this probability GIV. So of course you can imagine that the uniformly sync picking mechanism is a special case of this, but there could be more mechanisms, and we have a mechanism which is a non-trivial one and which is also strategy proof. Note that we'll have to be very careful while choosing this GIV so that it does not break the strategy proofness constraint. We cannot really arbitrarily pick a node just by looking at the valuation profile because that might break the strategy proofness constraint. For example, yep.
I'm missing a little bit the algorithm slightly, but it says output the probability distribution, and then kind of in the follow-up you're already calling the probability distribution. What's going on? You're already for I in n take this probability
well,
GI.
Just saying what's the output at the end of the algorithm.
Yeah, so
It's not a command, it's like the
No,
yeah,
I understand,
it's a
but then on the third line, you're already describing it, right? So how can you be calling GIV when you haven't kind of defined it yet?
So
if it's supposed to be the output of this algorithm.
So the first two lines is not part of the mechanism. It's just saying what is the input and what is the output, and this is how I am picking this output G. Is if I'm given the valuation and I'm deciding whether to make you sync with probability G1V, say. So this is a class. So if you want a specific answer, for example, for the case of uniformly at random, I'm picking GIV as 1 by n. So with probability 1 by n, I am picking every agent and treating him as sync. But you can do it a little in a more non-trivial way by, say, for example, I keep aside one agent as a default agent. So I first pick uniformly at random every agent, and with that probability I keep aside a default sync, and I look at the other agents and look at if there exists an agent whose maximum sweep, this minus m by 2 to plus m by 2, does not change the outcome. So suppose even if he could flip his valuation, so currently I am without that agent, I am going to choose A. Even if he changes his valuation from minus m by 2 to plus m by 2 for that A, still the outcome is not going to get changed because the sum valuation is already more than that. Then I can choose that agent as a sync because he will give me a 0 regret or 0 inefficiency. But if there does not exist, there could be a possibility that there does not exist any such agent, then I choose that default agent as the sync. This is exactly what I have informally presented here. So this is a case where you have a mechanism which is non-trivial and an example of a generalized sync mechanism. Yeah, and when I pick somebody as a sync, I do the very standard thing, pick the alternative that is efficient without that agent, and then transfer him the Clark's pivotal payment.
I think what's throwing you off is that, it's the question of what's input, what's output. There's kind of two steps. One is where the random bits come in.
No, so the question is where is G coming from?
No, I understand. Right, so the mechanism, the general mechanism outputs G, but when you run it, you get some random bits, and then you pick an agent from G with those random bits.
I'll take it offline.
Okay. Okay. So, yeah, so, and here comes that intuition. So, when you are, so this class of generalized sink mechanism is definitely larger than the class of that naive sink mechanism, but it does not do any better than the deterministic mechanism when you have a lot of alternatives. So, in particular, when M is larger than N, then every generalized sink mechanism has an expected sample inefficiency, which is as bad as the deterministic case. So, I'll present some of the intermediate results and say that a little informally. And it's kind of intuitive as well that when you increase the number of alternatives, the inefficiency can only increase because the inefficiency that you had for suppose M, if you increase one alternative, you can always append that with the very low valuations, which does not ever come in the context of being the optimal outcome. So the inefficiency remains the same. It can potentially increase, but it can never decrease. So in view of this result, we look at the other extreme case because we know that if there are many alternatives, it's going to have a very bad inefficiency bound. We look at the extreme case of M equal to 2. Only 2 alternatives. Now what happens? It's very easy to see that the random, the naive random sink, that is picking every agent with probability 1 by n, gives a sample inefficiency of 1 by twice n. It improves by a factor of 2. And now in order to look at what is the optimal mechanism, at least one specific case, we focus on the 2 agent and 2 alternative case and look at the absolute inefficiency where I am multiplying n because it does not really matter when we have fixed n. And in this metric, you can see that this naive random sink will give half, while the deterministic mechanism will continue to give 1 as the absolute inefficiency. And the result says that in the class of generalized sink mechanism, nobody can do any better than half. So in other words, in the case of 2 agents and 2 alternatives, naive random sink is as best as any generalized sink mechanism for this special case. So then we look at the case of 2 agents and 2 alternatives and formulate this problem as an optimization problem where we are trying to find the optimal randomized sink mechanism. And here is how we'll write it. Our objective is to minimize the absolute inefficiency, the difference, the loss in the social welfare, the maximum of that. And we are trying to minimize with respect to the mechanism, F and P. Now this mechanism has to satisfy certain constraints. The first constraint is the strategy proofness constraint. The second constraint is to make sure that this mechanism is a valid randomized mechanism. That is, it is non-negative and it sums to 1 for all alternatives. And then the last requirement is that the payment should be budget balanced. So you can reduce it to the standard. So this is a linear program. You can reduce it to the standard linear programming format for 2 agents and 2 alternatives. So where I have replaced the objective with L and replaced that L with the supremum. So essentially it should be greater than equal to this difference for every valuation, and that is what I have written over here. And for every agent, the first 2 bunch of inequalities are essentially the strategy proofness constraints for agent 1 and 2, and the rest of the constraints are similar, budget balance and the valid social choice function assumption. So even though we have reduced the problem into a linear program, you can notice that the number of constraints is essentially huge. We need the V1, V1 prime, and V2, which are essentially continuous. So it's a mapping from the alternative set to the open interval minus m by 2 to m by 2. So this number of constraints in this bunch of inequalities is essentially uncountable. So in order to solve this using the finite optimization techniques, we'll have to discretize the set of valuations, and that does not hurt. Why? If I now reduce, suppose instead of the valuation being a mapping to the continuous interval from minus m by 2 to m by 2, if I discretize into say k discrete levels, and then the number of constraints now become finite. From being uncountable, it becomes finite. So more number of f and p will start satisfying them. So essentially, the constraint set, the set of constraints gets reduced. So the feasible set increases. So the minima that I'll get in that discrete relaxed problem will be lower than the minimum in this context. And that should be fine. That we are actually trying to find a lower bound on the inefficiency. So that's the point of doing this discrete relaxation. And for the special case of 3 discrete levels, one can analytically find this the lower bound to be 1 by 7. Now you can think of the finer I make this discrete level, the tighter would be the lower bound to the actual problem. And that is the idea of automated mechanism design, and we do run this process for more number of levels. So here on the x-axis I have plotted the number of levels k, and the y-axis I have plotted the absolute inefficiency. The solid curves essentially denote the automated mechanism design or the optimization based approach, while the dotted lines are the theoretical bounds. For the deterministic case, both the theoretical bound and the AMD based approach overlap, because even for 2 levels, minus m by 2 and plus m by 2, you can create an example which achieves this minimum bound. For the generalized sink mechanism, in the case of 2 agents and 2 alternatives, the lower bound is 0.5 that we have shown. This red solid curve shows how this process of automated mechanism design is converging towards 0.5. And we do not have a theoretical lower bound, but we don't think that this is going to be as high as 0.5. And in particular, we also do not know the structure. So do not know the structure of this optimal mechanism, but it turns out that it is much lower than of course the deterministic and also the generalized randomized sink mechanism. So in summary, what we have is we have explored the interplay of inefficiency and budget balance in the context of deterministic as well as randomized mechanisms. For the deterministic case, we have a complete characterization of what should be the minimally inefficient mechanism subject to budget balance, and the fact that it cannot improve the asymptotic bounds for the inefficiency plus budget balance together. Randomization helps, particularly when the number of alternatives is small. So the future work remains to explore the structure of this mysterious randomized mechanism, which achieves this lower bound, the lower bound for the inefficiency subject to budget balance, and also you would like to understand how this rate of improvement of the optimal bound varies with n. So that's it. Thank you.
So in this mechanism, what basically happens is that you pick some person and you give him a huge reward in order to maintain the budget balance. In theory, I understand not always, but kind of. Let's think about it like that. Let's say that it's fairly high stakes, and everybody. You can create situations, right, when some person gets a huge reward. So
right.
if you guys considered situations where you don't, your objective is to make sure that everybody's utility is kind of sort of similar, or let's say that the utility is somewhat more fair, right? So fairness other than efficiency considerations.
So I think I think the fairness is not an issue whenever you are considering efficiency. So So in the efficiency is against the fairness idea, right? So you can have one agent for whom the valuation is arbitrarily large. You are picking still that alternative, even though that is bad for the rest of the population. So if you are going for fairness, you are already violating efficiency in some sense.
Okay, sure. Okay, well, you can also normalize utilities, right? You can also kind of assume that all utilities sum to the same value to kind of like to ensure that inherently, at least, like it's fair in that respect.
So.
Knowing kind of like, well, I'm sure you understand where I'm coming from.
Yes, I understand, but yeah. So I mean, whenever you have, so here the goal is to achieve the efficiency for every agent. So even though it requires a lot of money to be transferred to the sink agent, that's fine. But as long as, so it's making it budget balanced. So I'm not burning any amount of money, and I'm ensuring that it will not be super inefficient. In other words, it will be as minimally inefficient as possible.
No, I understand. I totally understand. I'm just asking about a new kind of like objective, which would be to ask, instead of doing these allocations that are extremely unfair in some respect, right? Could you create something? Okay,
I'm not sure whether there will be any feasible solution. I mean, you can pose that as a constraint in the optimization problem, right? So somewhere they are almost kind of similar.
Will have to go, right?
Yeah. So all the utilities have to be somewhere close by. Now I'm not very sure that whether that feasible set would be non-empty or not. So that's something needs to be explored.
I think there's another meeting happening here soon. So let's take the rest of the questions offline and return to our speaker again.